Okay, good. All right. Oh, yeah, question. We can't talk about quiz questions until 48 hours after the quiz. So on Monday, I'd be happy to answer that for you. But today, unfortunately, for whatever reason, no. But yeah, Monday, yes. Good. I guess before we get in to the math for today, are there any administrative questions? All right. Well, I hope the quiz went well for folks yesterday. And of course, we'll be getting those graded and whatnot, and grades released on Monday. And I'd be happy to answer any questions, come Monday. So then, why don't we transition a bit and go into our math? And so in today's class, we're still talking about mins and maxes, similar to what we did back in our Calculus 1 days, that you would talk about critical points and local mins and maxes and whatnot, and then you would have a class about absolute mins and maxes. So this is our class about absolute mins and maxes. In our Stewart textbook, it's all in section 7, but it's way too much to do in one class day, so we have our second class day here. And so I wanted to start off with, first of all, when can you actually find absolute mins and maxes, right? Because they won't exist for, just any old function on any old set sort of deal. And so in order to guarantee that you can actually win the game, that you can go out and find an absolute min and max, what you need is this extreme value theorem. And it says that, right, if we have a continuous function, first of all, and it needs to be on a closed bounded set. So already we need to have a few definitions of what closed and bounded mean. Then it has an absolute min and a max, right? And so the definition here about a closed and a bounded set, again, this is all in the pre-class stuff, so I'm not going to spend a ton of time on this. But yeah, bounded means that you can surround it in a circle, and closed means that it contains all of its endpoints or its boundary points. And usually this means if you have a drawing that you're going to be drawing it with only solid lines and no dashed lines, right? Because dashed means you go right up to it, but you don't include your boundary, right? We want to include our boundary. But, right, the extreme value theorem is nice and all that sort of stuff. It doesn't tell us how to actually find them. It says that, yes, they exist, they're out there, but it doesn't give us a technique for how do we actually find our mins and maxes. And so that's what this theorem right here is about. You need to find critical points. Then you need to find critical values on our boundary. And then we're going to list all of these out on a big list, similar to what we did in Calculus 1. Biggest of those is the absolute max. The smallest is the absolute min. So basically, we're trying to come up with a list of potential mins and maxes, right? And so we're going to be adding lots of points to that list and then evaluating. And then we did an example, and we'll do certainly more examples in today's class as well, but this is a relatively nice one to start with. So that is the pre-class video in a nutshell. Any questions about anything in the video that maybe wasn't especially clear? Yeah. Boundary points. What about boundary points don't you like? So, yeah, this is a technical definition, really that's maybe more appropriate in like a 300 or 400 level math class. But boundary points are going to be like right on the edge of a region, right? And so how do you mathematically define that it's right on the edge, right? Well, one way that you can do it is that if you draw a circle around it and you can allow for any radius, right, as small as you want, right, then that circle that you've drawn around it, which when you talk about a circle and all of its interior points, this is mathematically called a disk. So that's, in the boundary point, it says every disk. So no matter how small your radius is, the circle and all of its interior points, some of it needs to be within the set and some of it needs to be out of the set. Otherwise, you're not right on the edge, right? If you're just a little bit inside, then you can find a very, very small radius in which it's all contained within inside the set, right? I'm thinking about this picture here with the green little lima bean or something like this quite a lot. So if you're not on the very edge, you can come up with a very small disk, right? Still have a positive radius, all that sort of stuff, but a very small one that means that right? You're not on the very edge, right? And likewise, if you're not on the very edge and you're just outside, right? Again, you're not going to have necessarily some points of that disk inside and some outside. So it's trying to make sense of what do I mean by being right on the edge? But like I would say the intuition is probably the most valuable thing. So kind of understanding that the boundary points are kind of all these edge cases. That's the most important thing. All right. So with that, why don't we go ahead and try some new problems. So I'd like to find the absolute maximum and minimum values for this function on this rectangle. So, I mean, largely when a problem is given to you and says it wants you to find the absolute minimums and absolute maximums, it's pretty much guaranteed that, right, that the function and the region satisfy the extreme value theorem, that we have a continuous function and that we have a closed bounded set. Otherwise, right, it doesn't make sense to give you this as a problem. So let me go ahead, and what I like to do is typically draw the region. So my region has a set of xy. Again, this is a domain that we're going to be inputting into our function here. A set of xy coordinate pairs that x ranges from 0 to 3 and y ranges from 0 to 2. And there's lots of these less than or equal to signs, right? So we are including our boundary. So we can go all the way down to x is equal to 0, all the way up to x is equal to 3. And I'm staying within y should be no more than 2 and no less than 0. So this right here is my region D. I can trap it in a circle, and it includes all of its boundary points, right? I had to use solid lines rather than dashed lines. So yes, this satisfies the hypotheses for the extreme value theorem. And so yes, it makes sense to ask for an absolute max and an absolute min. So now I'd like to go about applying my technique for finding the absolute max and the absolute min. And so the first step that we'd like to do for this is find our critical points. These are the same critical points that we had in last class, right? That is, I want to start taking some partial derivatives and want to figure out when these are ideally both equal to 0, or if we can possibly make either one undefined. So if I take a partial derivative with respect to x, I'm going to get 2x minus 2y. If I take a partial derivative with respect to y, I'm going to get negative 2x plus 2. So there are my derivatives with respect to x and with respect to y. Notice these are nice continuous functions here. There's no way to make them undefined. There's no way that you can divide by 0 or take the square root of a negative or take 0 or the negative of a natural log, right? So these are just polynomials. So we have no chance of making these undefined, but hopefully we can make them equal to 0. So if I want to make, for instance, I notice this second one here only has x's in it. So if I wanted to try to make this equal to 0, that would require that x is equal to 1. So if I want my y derivative to be 0, the only way is if the x coordinate of those points are equal to 1. Okay, but remember, I want not only my y derivative to be equal to 0, but I also want my x derivative to be equal to 0. So this is going to say my 2x minus 2y needs to be equal to 0. Again, I've already found out, and I want both to be true. I want both my x partial derivative and my y partial derivative equal to 0. And the only way I get my y partial derivative equal to 0 is if x is equal to 1. And so therefore, I can go ahead and plug this in. And I'm going to get y has to be equal to 1. And so this tells me that 1, 1 is my critical point. And this is a point that needs to be added onto our list of potential mins and maxes. So at the very end, we're going to have collected lots and lots of these points, or maybe not lots and lots, but a good number. And then we need to evaluate our function at all of these. And the biggest is going to be the max. The smallest is going to be the min. The next step, and quite often the longest step, is checking our boundary. The problem with our boundary in this case is that it's made up of 4 pieces. We have the left side of our rectangle, we have the bottom of our rectangle, we have the right side of our rectangle, and we have the top of our rectangle. And there's no way to describe these kind of simultaneously with just like one nice equation or anything like this. We do have to go through each individual one of these and check each line and see if there are mins and maxes or potential mins and maxes on each curve. So let's start off with a relatively nice one. If I was to look at the bottom here, this is part of the line y equals 0. It's a nice horizontal line where I haven't gone up any and I haven't gone down any. Y equals 0. Now, of course, y equals 0 would normally go on forever, but on the boundary here, I'm only interested in when x ranges from 0 to 3. So that's literally my boundary right here that I'm interested in. So maybe my first thing, I'll just say that this is the bottom of my rectangle, and that has the equation y equals 0, and x ranges from 0 to 3. So on the bottom here, if I was to think about what is my function doing, well, I go back to my function, and everywhere I see a y, I can plug in a 0, because after all, on this boundary, y is exclusively 0. And so when I do this, I get x squared. So I'm going to get a function that just has x's now. And I am now back in my calculus 1 world, and I'm trying to figure out where could potential mins and maxes be for this, right? And if you wanted to do this back in your calculus 1 days, the way that you did this was you took the derivative. Now that there are no more y's, right? There are just x's. I'm taking an x derivative. And I want to find critical points for this one variable function, which means I'm interested in when this is 0 or undefined, which means that x equals 0 is going to be a critical point. Now remember, I'm on the line right now where y is equal to 0. So the full point here is going to be 0, 0. This needs to be added to the list. But just like we did in calculus 1, not only do you need to have your critical points, but you also need the endpoints, right? So this says here that x needs to range from 0 to 3. You always look at the domain to figure out what your endpoints are. So when x equals 0, we would have 0, and of course we're on the line 0. And when x equals 3, we would have 3, 0. Now, of course, we can see that we have included 0, 0 twice. In our final list, we won't include it twice. We'll only include it once, but it turns out to be a critical point and an endpoint for this boundary. Quite often what I like to do, and just make sure that I'm not forgetting anything, is that I typically like to draw these on my sketch, right? So I have here so far 0, 0, I have 3, 0, and I also saw my critical point was 1, 1. So these are my 3 points that so far need to be on my list. Okay, we need to play the same game a few more times. Oh, sorry, question. 3, 0 is not a critical point. 3, 0 is an endpoint. But endpoints, as you recall, are very important from calculus 1. Let's go back to our video really quick, because I had a nice picture. So yeah, if you're trying to find, again, in calculus 1, absolute mins and maxes, right? Absolute mins and maxes could be at critical points, right? But they also could be at the endpoints. And so we need to include both on our list, both critical points and endpoints, once we get into our one variable function, because there you could actually have our absolute minimum or our absolute maximum. And we don't know if it's there or not without testing. Good. Any other questions? Yes.
Why did you pick 0 as an endpoint and not like 3, 2 or anything?
Well, right now we are on the curve where y is equal to 0. So eventually we will get to 3, 2, and it will certainly be a part of our list. But for this bottom piece right here, we're only traveling from on y equals 0 from x equals 0 to x equals 3. So we're right now just gathering our potential absolute mins and maxes along this curve here. So maybe our next one, I'll go ahead and do the left-hand side. The left-hand side has our other 0, right? In this case, it's x equals 0. Y is going to range from 0 to 2. So when I plug this in, I'm going to get f of 0 comma y is equal to, and again, I'm plugging in 0 for everywhere I see an x, so I'm just going to get 2y. So this is a perfectly good function back in our single variable calculus. I can look for critical points on this, so I can take the derivative with respect to y, but I'm just going to get 2. And my question to you, what can I plug in for y to make 0 equal to 2? There's no way you can make that happen, right? No matter what you plug in for y, this is not the case. And so there are no more critical points to add from here. Sorry, question. So the question was, for the first one here, do we need to do the partial derivative to make sure that, to see that 0, 0 should be included, or is it enough to just grab it for the endpoint? And I would say that these problems are long enough. You'll see that, I mean, we're maybe halfway through right now, that it's pretty unlikely for them to show up as multiple choice or true false style questions. I've seen a lot of these as like standard response style questions, right? And for standard response, you're graded based on your method. And so if you don't take the derivative, right, and you just exclude that, right, well, then you haven't, like, that's the wrong method, right? You need to know if there are any critical points on this curve or not. And so, I mean, now that we have the answer and looking back on it, we say, okay, yeah, we wasted a little bit of time. We didn't find any additional critical points in this case, but I didn't know that to begin with. So yes, we need the derivative, right, kind of in order to get full points. No, you didn't need it to get 0, 0 on the list, because you would have happened to get it 0, 0 on the list in another way because it happens to be an endpoint. Yeah.
So not all endpoints are critical.
Correct. For instance, 3, 0 here wasn't a critical point, right? So yeah, not all endpoints are critical points, but all endpoints need to be included on the lists, right? Because they could still be potential mins and maxes. All right, so in this case, I don't have any critical points to add to my list on the left-hand side. However, I do have a couple of endpoints, and those would be when x is equal to 0 and y is equal to 0, and when x is equal to 0 and y is equal to 2. So again, I'm plugging in my endpoints of my boundary in this case, and recalling that I'm on the curve x equals 0. So of course, my x coordinates are always 0 on this curve. And if I want just the endpoints, that would be either when y is 0 or y is 2. So again, we see that we have 0, 0 again. That one's not new, but 0, 2 is new. So again, I like the picture just because you can kind of see which ones are new versus which ones were already there. Yes, question.
Critical points also be endpoints, because isn't that like isn't that not a derivative? You have one, the endpoints are never, they don't have a derivative.
So the question is about, can endpoints be critical points at all? Is essentially what I heard, right? Because typically in calculus 1, in order for the derivative to exist, it must be a limit as h goes to 0, and it's not a right derivative or a left derivative or anything like this. It's just the limit as h goes to 0. And so it's true that we have a restricted domain in this case, right? Because we're only interested in this box. However, the function, x squared makes perfect sense whether you're on this restricted domain or not. So, I mean, technically you could say that 0 here is not a critical point, or you could include it because, again, with it being an endpoint, it's making your list no matter what, right? And it's this, you would have to show the same work in order to check for critical points in either case as well. So yeah, I mean, I see your point. I just don't see how it saves us any time or anything like this. We still have to show all the same amount of work. Okay, we have 2 sides down. Let's do maybe the top side. So the top side, I'm going to include it over here. This is where y is equal to 2 and x ranges between 0 to 3. So in this case, I'm going to go ahead and plug in everywhere I see a y, I'm going to plug in a 2. So I'm going to have x squared minus 4x plus 4. You can barely see it up here, but this is my original equation, right? And again, I'm plugging in a 2 everywhere I see a y. So let's go ahead and try to find for critical points. 2x minus 4. This is going to be equal to 0 exactly when x is equal to 2. Since I'm on the curve y equals 2, that means that my point 2, 2 needs to be added to the list. We also need to think about our endpoints, right? So again, for the endpoints, we're looking at endpoints of the domain. So we have x equals 0, and again, we're on the curve y equals 2. And then we also have x equals 3, and again, we're still on the curve y equals 2 for the top piece here. So if I go up to my picture here, this is the first case where we get a critical point on our list that's not an endpoint, right? All right, we've got one more to check here. Let's maybe go down here. So this is going to be the right-hand side. This is when x is equal to 3 and y is ranging between 0 to 2. So we're going to have, again, plugging in 3 everywhere I see an x. So let's see, I'll have 9 minus 6y plus 2y. 9 minus 6y plus 2y. Again, looking at my original equation here and plugging in a 3 everywhere I see an x. So when I take the derivative of this with respect to y, with respect to its only variable here, what I'm going to get -4. And just as before, what y values could I plug in order to make 0 equal to -4? Well, you can't, right? No matter how hard you try, there's no solutions to this. And so we don't have any endpoints that we need, sorry, we don't have any critical points that we need to add to our list. However, we do have a couple of endpoints. So this is going to be when x is equal to 3 and y is equal to 0, and when x is equal to 3 and y is equal to 2. Those are already both on the list from before anyway. All right, so the bulk of the work, checking all 4 sides, is now complete. Last up, we need to plug in all these values into the function. Smallest is going to be the min, biggest is going to be the max. So we have here, what? 0, 0, we have 1, 1, 2, 2, we have what? 3, 0, 3, 2, 0, 2, 1, 2, 3, 4, 5, 6 points that I remember from my list. Let's look at my picture just to make sure. So I have 1, 2, 3, 4, 5, 6. Yeah, that looks good there. And again, my function is x squared minus 2xy. What is it? Plus 2y. So when I plug in both of these being 0, x and y both being 0, we get 0 here. If I plug in they're both 1, I'm going to get 1 minus 2 plus 2. So that gives us 1. If I plug in when they're both 2, we're going to get 4 minus 8 plus 4. That's 0. When I plug in 3 for x, 0 for y, that's going to give me 9. When I plug in 3 for x and 2 for y, what that gives me 9 minus, 4 times 3 is going to be 12 plus 4. So let's see, -3 and 4 is going to be 1 there. And then finally, when I plug in 0 for x and 2 for y, that's going to give me 4. Did I make any mistakes? Anyone catch any mistakes? Good. All right. So from this, we can see that the biggest number on the list is 9. This is going to be our absolute max. And our absolute minimum is going to be 0, it looks like. So remember, the extreme value theorem says that the absolute max and the absolute min are attained at least once. So you can get them only once, like the 9 there was, but it's possible that there may be multiple points that give you the absolute min or max, right? In this case, we can see at 0, 0, or at 2, 2, we get the absolute min. Any questions on this problem here? Yes.
Faster method
So the question was, is there a faster method or is this the only method? And I'm sad to inform you that this is the only method. Yeah. All right. Well, let's try another one. Absolute min and max. Let's go ahead and draw out our region here. It's the triangular region in the first quadrant bounded by and including the line y equals 9 minus x. So if you wonder where it crosses, right, if you plug in x equals 0, you get a height of 9 for y. And if you plug in y equals 0, you get an x value of 9. So it crosses at 9, 9. Well, 9 up top and 9 down here. So this is what my region looks like. We have a nice continuous function. So again, we can ask about absolute mins and maxes. Just as before, we can start off with finding the critical points. So this is just like we did last time. We need to take some partial derivatives, figure out when they're both equal to 0, or at least one's undefined. So if I take a partial derivative with respect to x, I'm going to get 2 minus 2x. If I take a partial derivative with respect to y, I'm going to get 2 minus 2y. If I would like this to be equal to 0, the only way that that happens is if x is equal to 1. And likewise, if I would like my y partial derivative to be equal to 0, the only way that this happens is if y is equal to 1. So skipping a few steps on solving that, but again, I would just move the 2x to the other side and then divide by 2. So this tells me that the point 1, 1 is my only critical point. So if I was to maybe start adding to the drawing over here, I might do something like this, just to show at 1, 1, we have a point of interest. All right, now we need to go ahead and move on to the second bit, which is checking all the boundaries, right? So again, we have 3 boundaries that we can see. The bottom one is going to be where y is equal to 0, x ranges from 0 to 9. The left side here is going to be when x is equal to 0, with y ranging from 0 to 9. Bless you. And then the, well, this is, I guess, a right triangle, so we could say the hypotenuse. The equation was already given to us, y equals 9 minus x. What would x range between? 0 to 9 again, right? So again, all the way from the top dot all the way to the bottom dot, that's going to be from x equals 0 to x equals 9. All right, so let's go ahead and do the bottom piece, like plugging in 0 for things when possible. So let's get all the easy ones done. So when y is equal to 0, our function looks like 2 plus 2x minus x squared. I can take the derivative of that, and I can figure out where we have critical values along this part of our boundary. And it looks like we're going to have when x is equal to 1. Of course, we are on the curve y equals 0 currently, right? So that means that the point 1, 0 should be added to our list. We can also add our endpoints at this time. Those are going to be 0, 0, and 9, 0. So I can go over to my picture again. 0, 0, 9, 0, and 1, 0. Those are all my points of interest that are along that bottom curve. Next up, let's do the left-hand side. This was where x was equal to 0 with y ranging from 0 to 9. So when x is equal to 0, our function looks like 2 plus 2y minus y squared. And just as before, we need to search for critical values here. So I'm going to take the derivative and solve when does that equal 0. This is going to give us y equaling 1. And again, remember, we're on the curve x equals 0. So that means that the point here is 0, 1. We also need to include in our endpoints. So we're going to have, 0, 0 and 0, 9. So let's see, 0, 0 is already on there. 0, 1 is right here. 0, 9 is on the top. All right, one more to go. I guess I'll call this hypotenuse. That was where y is equal to 9 minus x, and x is ranging between 0 and 9. So my function, and again, I'm going to be plugging in everywhere I see a y, I'm going to be plugging in 9 minus x. So I get down to just a single variable function. So let's see, I'm going to have 2 plus 2x plus 2y, but again, I'm going to plug in 9 minus x, minus x squared minus y squared. But again, I'm going to plug in my 2 minus x. Yeah, it is. Thank you. 9 minus x. I'd like to believe that. I would have caught that eventually. All right. And just as before, we need to search for critical values. So I'm going to go ahead and take the derivative. There are only x's here. So let's see, I'm going to have 2 plus 2 times negative 1. So let's see, I'm through this bit here. And then next up, we have a negative 2x. That'd be that piece. And then this one, there's a bit of a chain rule, right? So there's a negative 2, reduce my power by 1, and then multiply by the derivative of the inside. So something like that. Again, I'm going to be trying to solve for when is this equal to 0. That'll help me find my critical values. So I can see that there's a little bit of cancellation that happens here. But let's expand out the rest of it. I guess we can see that there's 2 minuses. So those can become plus. And so let's see, we're going to have negative 2x plus 18 minus 2x. And so what we get, 4x is equal to 18. And so that gives me x is equal to 9/2. In order to figure out what the y value is, well, on this curve, we have y is always equal to 9 minus whatever the x value is. So in this case, I'm going to have y is equal to 9 minus 9/2, which means that y itself is going to be 9/2. So that means I have a few points that need to be added, right? 9/2, 9/2. And also my endpoints. So when x is equal to 0, I would have y is equal to 9. So 0, 9. And then when x is equal to 9, y would be equal to 0. So going back to my picture, 0, 9 and 9, 0 are already on there. But the 9/2, 9/2 is not on there. So 9/2, 9/2. That's like 4.5 right in the middle there. All right, well, we've done the hard bit here. Now let's go ahead and write all these out and figure out which is the largest and which is the smallest. So I had what, 0, 0, step 3 here, 1, 0, 0, 1, 1, 1, 9, 0, 0, 9, and 9/2, 9/2. 1, 2, 3, 4, 5, 6, 7 points. Let's just go back here really quick and make sure. 1, 2, 3, 4, 5, 6, 7 red dots. So yes, it does look like I remembered them all. And again, the function that I'm plugging these into, 2 plus 2x plus 2y minus x squared minus y squared. So when x and y are both 0, we just get 2. When x is 1 and y is 0, what we get 2 plus 2 minus 1. So that's going to give us 3. Likewise, when x equals 0 and y equals 1, we're going to get very similarly 2 plus 2 minus 1. So again, a 3. When they're both equal to 1, 2 plus 2 plus 2 minus 1 minus 1. So let's see, 6 minus 2, that's going to give us 4. If x was equal to 0, sorry, if x was equal to 9 and y is equal to 0, we're going to get 2 plus 18 minus 81. So for what? Minus 61. Likewise, if x is equal to 0 and y is equal to 9, we're going to get 2 plus 18 minus 81 for, again, negative 61. And then finally, 9/2, 9/2. 2 plus 9 plus 9 minus 81/4 minus 81/4. So what? That's going to be 20 minus 81/2. Anyone with a calculator want to help me out and give me a decimal? Good. Good. There's some agreement too. Negative 20.5. So it looks like our absolute max is going to be at 4. And our absolute min is going to be negative 61. By the way, so you have to be a little bit careful, right? When I ask for what is the absolute max or what is the absolute min, those are the function outputs, right? So 4 is the absolute max. The absolute minimum is negative 61. You can also ask, where do they occur, right? In this case, the absolute maximum occurs at the point 1, 1, and the absolute minimum occurs twice, once at 9, 0, and once at 0, 9, right? So just be careful about the wording of questions and make sure that you're answering the one that's given to you. I thought I saw a hand raised. Is there any questions about this? Okay. Well then, I have ideally, if we can get through this problem here or close to it, that would be good. I wanted to maybe point something out to you that when you have lots of boundaries like we've had, right? We had a rectangle which has 4 boundaries, and then we had a triangle which has 3 boundaries, right? Those take a while, right? Because you have to check many boundary curves. So consequently, right, if you don't want basically an entire quiz to take up, one problem to take up an entire quiz, an entire 30 minutes, probably having fewer boundary curves has some benefit because, right, you're not really gaining any new information to see whether or not a student knows to check the boundaries and all that sort of stuff if they do it once or twice versus if they do it 4 times, right? So pointing out just like the pre-class video, really quick, where we had a function that only had 2 boundary curves, right? It was trapped between a parabola and a line, right? This is a little bit more reasonable for a time setting just because, again, there are fewer boundary curves, so it's a little bit faster, right? So you're not having as much kind of overlap. And then this one right here, if I was to draw out the domain that we're interested in, this is going to be a circle of radius 4. So we're on the disk, x squared plus y squared is less than or equal to 16. Right? So we have the circle of radius 4 and all of its interior points. Because it's less than or equal to 16, right? We are including the boundary here. And so this is a nice closed set. And of course, it's bounded and all that sort of stuff. So yes, we can ask for absolute mins and maxes. So I would like to give you guys maybe 90 seconds or so to start this one. Find me the critical points. Find me a function that gives me the boundary. In this case, there's only one boundary curve, so it's going to be much faster than maybe some of the previous ones. And then finally, of course, the end goal is to give us maximums and minimums. So please, I don't expect you to get all the way done, but I want to at least give you a head start to please at least get some critical points for us and start to think about what's the boundary curve. So I'm hoping that you guys got to at least this point here. Maybe have started to think about a little bit how to get our function's value on just the boundary. So when we find the critical points, I think the only critical point here is 0, 3. So I've added that to the picture there. Maybe I can write it down here to make sure that I remember to add it to the list as well. On the boundary, right? When we're talking about the boundary itself, that's going to be when x squared plus y squared is equal to 16. That's when we stop, right? And so likewise before, I mean, we had all of these interior points as well, right? But on the boundary, this was when y was equal to 0, not when y was equal to 1 or 2 or anything like that. or when x was equal to 0, or when y was equal to 9 minus x. So the boundary equation in this case is the circle of radius 4. X squared plus y squared equals 16. And so now we have to figure out, I would like to get my function equation either all in terms of x's or all in terms of y's. That's my end goal, because then I'll have just a single variable function that I can take the derivative of. Now, if I was to try to get this all x's, right, that means that I would have to do 2x squared minus y squared. And I go over to my boundary equation, and on the boundary, I do know that y squared is equal to 16 minus x squared. So I could go ahead and do minus 16 minus x squared, right? So that's me swapping in, instead of y squared, I can put in the boundary equation to get that in terms of x's. But then as I go on, I have to do plus 6y. And that square root's got me a little bit scared, right? Because in order to get this as y equals, I need plus and minus the square root of 16 minus x squared. And so I'd have to break this up into two different pieces, the top piece and the bottom piece. And that's, well, time consuming and annoying, right? Because I was just saying it's so nice that I only have one boundary equation. And now you say I have to have two, I have to have the top and the bottom. And so overall, I mean, this is okay, we could do this, but I'm a little bit sad. My claim is that if we get it all in terms of y's instead, it's a bit nicer. So let's go ahead and try that. So if I was to get all y's, that means 2x squared minus my y squared minus plus my 6y. So right, I need to swap out my x squared here for some number of y's. And according to my boundary equation, we know that x squared is equal to 16 minus y squared. So 16 minus y squared. No square roots required. So now this function right here works for any y values. And so this is the one that I'd like to go with. Take the derivative. Let's see, I'm going to have a 2 along for the ride, and then when I take the derivative of the inside here, we're going to have negative 2y. And then let's see, there's another negative 2y and a plus 6. So this is going to give us what? Negative 6y plus 6. And if I'm looking for critical values, that means that I want to set my derivative equal to 0. So this happens exactly when y is equal to 1. But I have to remember I'm on my boundary, right? And so if I need, what are the x values? Well, I know that x squared is going to be equal to 16 minus y squared. So that gives me that x squared is equal to 15, which means that x is equal to plus or minus root 15. So there are 2 points. That's better than having to do all the derivatives and all that sort of stuff twice. So at a height of 1, go over until I hit my boundary point over here, and go to the left until I hit my boundary point. So as of right now, I see 3 points. My claim is that I'm missing 2 of them. I'm missing 2 more points that I have not written down yet. Can anyone tell me what they are? I'll give you a hint, they're endpoints. That's close, yes. So that they are the endpoints. And the endpoints, again, we have to write down, and it's I did this on purpose, but if you're going too fast, I've seen students make this mistake, so I want to emphasize it, right? Once we've said that our function is going to deal with y's, right, and we've decided to go f of y here, right, we need to know what y ranges between that keep us on this boundary. And those y values are, well, the smallest y value is at negative 4, all the way at the bottom, and the biggest y value is all the way at the top, y equals 4. This turns out to be exactly the same as saying x equals 0. So we need to include in the top and the bottom parts as well. So I do see that I'm a bit over. And so this is probably a good place to stop. But usually the resounding question that I get when I say you need to include the top and the bottom is, why don't you have to include in the left and the right then, right? And it's because, right, our function was with respect to y. And so our boundaries of y, right, have y equals -4 and y equals 4. If you were to set this up with the x equals, you're right that you would include the left and the right as your endpoints, but it turns out these are not the mins or the maxes. And so this has actually saved you a few steps by excluding those. But if you decide to, play it safe and you include those points, right, and you check those, again, you'll see there's not mins or maxes there, but you can do that and there's no harm in it, right? There's no harm in checking other extra points, except for that it just costs some time. So, all right, thanks. I'll finish up this problem and give you the full solutions on D2L. Post those by 4 o'clock today. I hope you guys have a great weekend, and I will see you Monday.